Hello community, the best AI new research papers. Here we go. Monday morning. LLMs still cannot plan, but can large reasoning models. Let's have a look at OpenAI 01. And we have here a study by the Arizona State University, and they said here, this ability to plan, to set multiple actions in a logical, coherent way to achieve an outcome to a task. This is what AI should be perfect at, no? Well, they examined this and they have a lot of tests and they still say, hey, state-of-the-art LLMs still cannot plan. And they say, we also find that contrary to previous claims, one-shot prompting, and we talk about this in a minute, is not a strict improvement over zero-shot prompting. And they say in our tests, hey, for many LLMs, it seemed to do significant worse if you provide a one-shot prompting examples. So better go here with a strict zero-shot. So this is what they say especially notable for the Llama family models. Interesting. But let's look here at the official results that they found. Now, as you can see here, on the x-axis we have the length of the planning that an AI is able to do, and on the y-axis you have the correctness. Now you see that here there is a perfect 100% independent of the planned length, and this is achieved by fast downward. More about this in a second. But what I wanted to show you is here the performance of classical LLMs. And you see here the blue line, and the blue line is OpenAI 01 preview, and the red line, you guessed it, it is 01 mini. So those are here the best two models if you go about long context planning, long context action that will lead to the result about reasoning, causal reasoning, or logic. All the other LLMs like Llama and whatever are somewhere here close to zero. So I think quite some interesting information, but you might say, hey, what is this here on top here? What they call here fast downward. Now, never mind, I went there and I found a paper, it is from Multi-modal here of September 2011, and this is a fast downward planning system here, originally from 2006, my goodness. So this is here a classical planning system based on heuristic search. Highly interesting article. They go here in detail and explain here the working of this particular model. Of course, 2006, it is not an AI model, but you see the power if we have access to other kind of logic and to have maybe a classical model. However, if you want to go with AI models, you see 01, 01 mini and the rest of the LLMs for planning context length, looking ahead for real complex tasks. But this is it, and we go on to the next one. Beautiful next publication. We have here Microsoft Azure AI, Monash University and Fudan University. Can we only use guidelines instead of these few shot prompts here? So, you know, we have two possibilities. We have here the shot methodology, few shot chain of thought, for example, in our prompt engineering, or we explicitly say, hey, those are the guidelines. So we instruct the model to reason by the following guidelines here, and you need some task-specific knowledge, of course, that it is a coherent argumentation. And now the question here is, can we propose a framework to automatically learn here task-specific guideline from our datasets? So this would be great. You just put in a dataset and the system understands what is the domain-specific knowledge, what are the task-specific guidelines, and the computer will come up, our AI agents plural, will come up here with some guidelines. So how does it work? So we have the feedback, the guideline, and the tree gather agents. First, the feedback agent is designed to evaluate the outcomes, either right or wrong, of each question and answer to gather here some insights guiding here more efficient optimization strategies. Next, the guideline agent, agent number 2, is tasked with deriving guidelines from each piece of feedback and storing them in the local memory. And then, number 3, the tree gather agent aggregates here all guidelines hierarchically through a tree structure, ultimately obtaining here all unduplicated guidelines from a global perspective. And then, yes, you got it, you have your new guidelines. Okay, interesting work. Automatic prompt improvement included. So if you want to have a look at this, I think quite interesting. But we go on to the next paper. And this is now about LLMs. And now how can we forget old data? Data that is not correct, that is still in our LLMs. It was in the pre-training data. It was in the fine-tuning data. And now we want here to unlearn our LLM. This old wrong information should be washed out here of our AI systems, of our AI agents. And here we have the study here, New York University Capital One. How can we do this? And they demonstrate this here on a Llama 2 7B, a real old model. And they say, yeah, it can work. There is some significant forgetting on the unlearning data set. So there is a way, maybe a first way only, to have some unlearning of old, outdated information. On we go. Now, this is something beautiful, the impact of feature embedding placement here in the ansatz of a quantum kernel. And yes, you got it. We are here in quantum embedding kernels. We are here at quantum machine learning, a target kernel alignment here for quantum physics. So if you're preparing for my next endeavor on this channel, you know exactly we will talk about quantum AI. But let's go to the next one, and this is a much more down to earth. We have here Georgia Institute of Technology, University of California, Berkeley, and IBM Research, and they talk about a more efficient neurosymbolic AI. So they have now a detailed look and say, hey, what is the current architecture? Is it possible to optimize this? And they, as it turns out, oh yeah, there's a lot of things to optimize. So here you see towards a human-like cognitive AI here with the neurosymbolic AI algorithms here. And they look here at the interplay here at CPU, GPU, accelerator, the layer optimization here, the co-design for vector symbolic architecture, and what they do. Oh no, let's have a look what they found. Recent neurosymbolic systems have demonstrated great potential in collaborative human AI scenarios with reasoning and cognitive abilities, which is great. And now they say, hey, we aim to understand the workload characteristic and the potential architectures for neurosymbolic AI. How can we optimize neurosymbolic AI? And they systematically categorize here the algorithms and then experimentally evaluate and analyze them in terms now of runtime, of memory, of computational operator, of sparsity, of system characteristics, CPU, GPU, and so on. And their study revealed that the neurosymbolic models, they suffer. They suffer from inefficiencies on off-the-shelf hardware due to memory-bound nature of vector symbolic and logical operation, complex flow control, data dependency, sparsity variation, and limited scalability. So, hey, we have to optimize here our complete system much more to have a much better neurosymbolic AI. Nice, also done by IBM Research. And we go on. Now, this is an interesting one. This is about here a cooperative resilience definition in artificial intelligence, but not in a single system, but in a multi-agent system. Real nice. If we have stress, each agent in our multi-agent system will feel, is it still scale? What about the scalability? What about the robustness of our agent? If we increase the workload, if we increase everything, we put more stress on the system. How resilient are single agent and how is the system if it consists of a multi-agent system? And they at first define, hey, we have to propose here a clear definition what it means cooperative resilient in a multi-agent system. And then they have one or two tests to find out about it. And they have a very nice idea. Yeah, they start really simple. But then here, this is the diagram illustrating the proposed methodology for measuring now this cooperative resilience in multiple stages. And they look at this and they try to understand the complexity and the interplay of agents if you put a lot of stress on the system. And it's a real nice study. And do you know what? I was blown away because our authors here are from the Universidad de los Andes in Colombia. So hello to all our colleagues over there. Great to see here this publication by you. value. AI should provide value. AI should provide value for everybody. Let's take here a look for a medical task that might affect you as a human being here. Let's say you have, if you want to have a condition, let's say diabetes. And now the age-old question is, hey, can we use here adapted LLM models here to help us here with our immediately real-time analysis if you have specific medical conditions? And what is so nice here, they develop here a specific LLM for diabetes. They explain exactly what they do, they examine everything, and you know what? They have here the code available for you. If you want, I give you the link here to the original code so you can have a look and also at the model. So there is a movement here for medical tasks that will affect each and every person who has a medical conditions. Now they're really working here on their first AI implementation to help everybody if you have this thing. Now, of course, we have to play. We are here with Meta, and Meta says, hey, yeah, we have to offer something here to our customers on Facebook or on our clients on WhatsApp or wherever you are, on whatever platform by Meta. So what we do, we improve now, imagine yourself. So your image generation, and we go here to the diffusion models, and now they have here a new idea and they address the current limitations here, and they generate here for their platforms a new synthetic pair data generation mechanisms. They have here a fully parallel attention architecture with 3 text encoder and a fully trainable vision encoder to improve here the text faithfulness. And if you look at this, it's rather nice. So you have here 1, 2, 3, 4 persons, all beautiful. And now you can live your dream. Now you can imagine yourself by Meta. So you can have yourself as whatever this is or whatever this is. I have no idea about those. Those seems to be an astronaut, a pirate. So your ego, whatever you are dreaming of, just go to a Meta platform and there they will offer Meta AI for your ego and you will spend more time on their platforms. And now you understand why Meta is doing this research. But now let's be scientific because, hey, we have to guide here the identity of our persons, of the humans. So here's a universal framework for combating here facial manipulation via breaking the identification. And they say, hey, there's a misuse of deep learning-based facial manipulation, and this poses a threat here to civil rights. And you might say, what a coincidence that at first you have Meta and now you have this study. Yeah, I don't know, it just happened accidentally. And they now have here a study and a methodology. And they simply say, hey, we want to fight here deepfake. We want to fight here facial manipulations here on the internet. They say, hey, we want to protect your identity. It's all about multitask learning, NLM, and they have here a specific model developed. So if you're interested, you see here both sides. If you want to learn more, you know where to go. And if we talk about learning this is something you should not miss. This is here September 20, 2024, a more computation efficient fine-tuning methodology with HADAT updated transformation. And you might say, yes, of course, I understand. Because up until now, you remember, with our existing PAFT methodology, remember the low-rank adaptation, the LoRa modules that we used, and the LoRa adapter that we used more or less across the bench. Now, you remember that we had here this incremental update, and I have 3 videos on PAFT and on LoRa explaining this. And now they come up here with a new mathematical operation. And they say here, yes, most PAFT methods such as LoRa use incremental updates, which involve adding learned weight matrix increment to the original parameters. And they say also effective, these methods face limitation in capturing more complex parameter dynamics and do not maintain a strong correlation between the original and the updated parameters. And they say to overcome these challenges, we propose now a direct updated transformation paradigm, which constructs the transformation directly from the original to the updated parameters. Highly interesting, they go with the HADAT matrices, the HADAT update transformation methodology, and this is nice. I just scanned the paper. This will be a paper for my afternoon, and it is a beautiful Monday morning, and you see, what else? Our new AI research paper. And here we are. Scalable multi-agent reinforcement learning for a very specific task for factory-wide dynamic scheduling. And you would say, what this is about? And then you read, Intel Corporation. I see. So if you want to optimize here your factory dynamic scheduling of all the 100 or 1,000 tasks that are happening in a production facility, you ask, hey, is there a scalable multi-agent reinforcement learning methodology that we can increase if we have challenging tasks? So Intel here applied here a leader-follower multi-agent reinforcement learning. You know the MAL concept. I have 5 videos on MAL. If you're interested, just put it in the search term to obtain here a desired coordination after decomposing here the scheduling problems into a set of sub-problems that are handled by each individual agent for scalability. So you see, again, this is the old-fashioned concept. We have a complex task, then we divide this complex task into little subproblems. We give each little subproblem to a specific agent that hopefully has been trained on this subproblem. And then we hope if we bring all the pieces together, that then there is a solution, and we completely misunderstand that some complexity have a complexity that you just cannot divide up into simpler problems. But hey, who are we to help Intel in their factory-wide dynamic scheduling optimization? We just go on because we want to learn new stuff here, and we go on to Chainbud. Chainbud, yes, it is the last one, don't worry. This is an AI agent system for helping you to generate pipelines if you use LLMs. And we all had this. We say, hey, we start here with a blank new page. We're in front of a white paper and we have no idea how to build our LLM data pipelines, our input pipelines, our reasoning pipelines, our complexity pipelines. How do we do this? And now here, University of Montreal, yes, beautiful, thank you. They give us here this Chainbud. And if you say, hey, what chain is it? Myself, I had to look it up. It is Chainforge. It's an open source visual programming environment for prompt engineering. Great, but let's go there. So this is the base that they use. And as you can see here already on the workflow description, they have here also a Python evaluator and a Python environment. So you understand immediately what they're talking about. You have here some computational power in the background. And what I wanted to show you is they have here a multi-agent system. And no, this is not what I'm looking for. Here we are. And they have multiple agents. And the first agent, if you want, is a requirement gathering assistant, an agent. Because the system says, hey, great, you're sitting in front of an empty piece of paper. So what do you want to do? What is, and now here we go, what is your primary goal? What are then, if I understand what is your goal, says the AI agent, then I can understand what is the list of requirements that I need to build, how many agents I need to build, the complexity of the agents I need to build. What are your preferences? Do you want to go with Rust, with Python, whatever, TensorFlow, or you want to go with PyTorch, or whatever you need? And then also, they come up here with a suggested chain of thought strategy. But wait for the video here, my next one, because maybe chain of thought is not the optimal strategy, but never mind. This is here the requirement gathering assistant. So it probes you to understand, hey user, what do you want that I built for you? I built everything for you. I have so many thousands and thousands of data to build those pipelines. And if you interacted with this and the AI understands it, says, beautiful, now I activate here the planner agent. And the planner agent, understanding here the task-specific agent, the node data, the connection data, and the merge data, and how we do this, they are now doing the planning. And you remember that my very first paper today that I showed you here, we were talking here about what? About planning, the planning process, what actions to take in what logical sequence that we reach here a solution for the task real fast. So we end here this overview with a new research showing here how to optimize a planner to build for you LLM system, multi-agent LLM system, and they are built by multi-agent system, which is so beautiful. And of course, this is a cycle. They have a beautiful study if you want to go there. They give you more information. They give you some nice example that you see the explicit workflow. So, hey, maybe why not try it out? Those were the research paper. I read more than 250 papers today. Monday morning, I spent more than 3 hours scanning through all of them. But I think those are the papers you should know about. You should have read maybe in the late afternoon, so you are up to date with the latest information on artificial intelligence. This was here a pure experimental video. Tell me if you like it. Tell you if you have some questions. And yeah, if you want to have the link to all those videos, you know, in my YouTube channel, you just go to community. And as you see, 27 minutes ago, I published here exactly the title here with all the links to this original publication, a AI research publication, and there you have all the information. Let's see if you like it. Maybe this will become here a service here for my subscribers. I hope you enjoyed it. I hope you had a little bit of fun. I hope there was some new information for you, and it would be great to see you in my next video.